Good evening, all. Okay, fine. So let us start this session. Okay, guys. Just keep that. This is the today only we are going to start sequential circuit, right? Just left that part that we have done in our last class. I will teach everything from the beginning itself, right? Fine. See what we are going to do in sequential circuit. As I said, sequential circuit, it is there are no big difference, right? In combinational there is no memory, whereas in sequential circuit we will have memory, right? So combinational circuit plus feedback will give us a sequential circuit, right? So usually what are the major applications of the sequential circuit, right? As I told you already, the thing is in sequential usually we are trying to insert the one more term that is called memory, right? So whereas in combinational circuit we left over one term that is called, that is your combinational circuit la namakku enna illana there is no memory, right? We are unable to store the data, whereas in sequential circuit we can store the data, right? So wherever you want memory system, that is எங்கெங்கெல்லாம் உங்களுக்கு memory தேவைப்படுதோ அங்கெல்லாம் we can just go up with what sequential circuit, that's all, right? So its application is we are going to design, right, flip-flops, right? First combinational circuit la, that is the one of the major application is flip-flops, and then we are going to design counters, that is one type of application, and then we are going to design registers, right? Especially this register we are going to use it in microprocessor, that is the most application, right? That is most important application. And then in clocks also we are going to use this what I can say sequential circuit, right? So wherever there is a need of, right, memory, we are giving priority for sequential circuit. If we want to perform the present operation, then we are giving priority for combinational circuit, that's all. So let's start our journey from the beginning, right? So I said sequential circuit in the sense, right, we have to consider combinational circuit with many inputs and many outputs, right? So this is going to be our combinational circuit, right? So let us consider combinational circuit, right? With this we are going to connect a feedback, right? We are going to connect a feedback. This feedback that is combinational circuit with the feedback is simply called what? Sequential circuit. This whole set is simply called sequential circuit, right? Of course this is going to be feedback. This is going to be our feedback. This whole set is simply called sequential circuit, that's all. Now what are the applications, right? Its major applications are, we are going to design, first of all we are going to design flip-flops, that is memory circuits, and then we are going to use it in registers, right? And then we are going to use it in clocks, right? We are also going to use it in counters, right? We are also going to use it in counters, and separately the major application is we are also using it in microprocessor, right? So I can just put etc, right? We can also see the devices that we are going to design, analog to digital converter and digital to analog converter, right? In general all type of converter circuits we are going to give priority for combinational circuits, sorry, sequential circuits only. With the help of sequence only we are going to design all these type of circuits, right? So let us design. The first circuit that we are going to design in sequential circuits is simply called latches, right? Let's start our journey with the first primary circuit, right? Anyway, in order to design the sequential circuits, the priority will always be given for universal gates, right? The priority will always be given for universal gate. Why? Because, right, with the help of universal gate we can design what? All type of whichever the desired output that you want, you can get that one with the help of what? Universal gate. Whereas universal gate in the sense we are calling, there are two gates, one is our NOR gate and another one is our NAND gate, right? So either you can design a circuit with the help of NOR or you can design your circuit with the help of NAND gate, right? So totally we are going to use two type of separate gates in order to design the sequential circuit, right? So the first sequential circuit that we are going to design now is simply called latches, right? Now let us see. In order to design the latches, either you can go up with the NOR gates or you can use NAND gate. There are two possibilities, right? So first, let us design the latches with the help of NOR gate. Let us see. Here we are going to take two NOR gates separately, right? And we are going to design the memory circuit. That's all. There are no things to discuss. Just we are going to design the memory circuit, right? So let us see how to design. In order to design the latches, that is with the help of NOR, I'm just requesting you to take two separate NOR gates. First consider two separate NOR gate, and then we need cross. That is, we are going to cross couple them, right? So those two NOR gates will going to be cross coupled, right? So that is the cross coupled NOR gates are going to act as a latches, right? Are going to act as a latch, right? So let me call them. Here we are going to consider two names. I said, so this is called reset and this is called set, and the outputs are simply called Qn plus 1 and Qn plus 1 bar. In sequential circuit, usually we are having two type of outputs. One is Qn plus 1, it denotes the present output, whereas Qn plus 1 bar, that is called what? Complement of the present output, right? And whereas we are also using one more term that is called Qn and Qn bar. If I will use Qn and Qn bar, right, here, if I will mention, right, in your circuit, if you find any term is called Qn plus 1, Qn plus 1 அப்படிங்கிற term நீங்க find பண்ணும்போதெல்லாம் அதுக்கு முன்னாடி, right, அந்த இடத்துல Qn is acting as a what? It is acting as a passed circuit, that is passed. In general, while designing the flip-flops, your output is simply represented by Qn only. Qn and Q bar only we are using. Guys, listen, I am repeating. If you find Qn plus 1 in the output port, right, Qn plus 1 இருக்கும்போது மட்டும் Qn, you can just treat this Qn as the past. Suppose in your output, if you are finding Qn, direct Qn தான் இருக்கு அப்படினா, just you can proceed the operation. You don't need to consider whether it is present output or past output. Don't think always that Qn denotes past and Qn bar denotes past output complement. Not like that. Whenever I am going with the Qn plus 1, I am just considering. In order to consider the previous bit, Qn plus 1 is present in the sense. What about the previous one? Just one step go back, Qn. That's all. That is acting. That will act as a, see that Qn plus 1 in the sense, இதுக்கு முன்னாடி இருக்க state யாரா? Qn plus 0. That is called simply Qn. That is called past. So whenever we are considering Qn plus 1, under that condition, in that condition only, Qn is simply treated as the past one, right? Yeah. Let us consider. Now our target is, we have to design the truth table for the latches, right? So anyway, whichever the circuit that we are going to design in sequential circuit, it is as per the same procedure that we were used to design in our previous cases at all, right? So step number 1, we have to realize the logic function, right? And then we have to frame the truth table, that is the primary function, right? So here first we had realized the logic gate, that is called cross coupled NOR gate. Now immediately the next step, you will have to design the truth table for this circuit, right? We have to design the truth table, right? Now in this truth table, we are considering two inputs. One is called reset, another one is called set, right? I will let you know why I am considering reset and set here, right? And we are going to consider two outputs, right? One is Qn plus 1 and another one is Qn plus bar. It is not necessary that you have to consider Qn plus bar also. Qn plus 1 is going to be our primary output. You no need to consider this one. Anyway, for our primary understanding, for few circuits, I will consider Qn plus 1 bar also. Later, we will ignore that one, right? So first, so just we are in the beginning. In order to get the clear idea about sequential circuit, I am considering both states here, right? So let's start our journey with this. Now, before starting this output logics, right? Starting determining this output logics, we will have to remember one more thing, that is the truth table of NOR gate. Now in NOR gate, usually we are having two input terminals with a NOR gate, right? Now if I will consider A and B as the output, then what about its that is what, sorry, A and B are going to be the input, output Y is going to be what? Say let us consider A, B, output Y, such that 0 0 0 1 1 0 1 1 we are going to consider. Is it visible to you all? Yeah, that is visible, right? And its corresponding combination for NOR gate, 0 0 will give you 1, rest of all are going to give you 0. That is the basic truth table that we are realizing for NOR gate. Exactly, that is true, right? Exactly, that is true. But the thing is here, we have to keep one thing in our mind. See there, in order to obtain output as 0 in case of NOR gate, at least one minimum high enable pin should be required. Listen guys, if you focus the output of the NOR gate, if all input pins are going to be 0, then output automatically will become 1. Whereas in the rest of cases, the beautiful thing that we are observing in case of NOR gate is, if I'll find any one high enable pin, at least one high enable pin, input pin, right? So active pin, input la vandu 1 அப்படிங்கற term நீங்க எங்கயாச்சும் find பண்ணிட்டீங்கன்னா automatically you can set that the output of that NOR gate, specific NOR gate, is going to be 0, right? So the conclusion is, sir, I am having n number of inputs for a NOR gate, whereas I don't know all inputs, but only one input are known, whereas rest of inputs are not known, but you can say your output is going to be 0. That is the basic thing that we are realizing in case of NOR gate. Clear? That's all. Now coming back, now see there, here we are considering two inputs, right? One is R, another one is S. So for this R and S, we can give 4 type of combinations, right? So first one, right, see R and S means in Boolean variables we can realize 4 combinations: 0 0 0 1 1 0 1 1. Let us consider all its possible combinations, and we shall try to estimate its correspondent outputs also, right? Let's try and figure out them. So case number 1, I would like to enter 0 and 0 here. Now the thing is, I only told you, while going along with the NOR gate, if I'll find minimum one high enable pin, automatically I can guess the output of the function is going to be 0 only. That is accurate answer. But the thing is, if your inputs are going to be 0 0, then your output is, you are unable to predict your output, because I don't know, when I am having 0, its exact output is not known for us. But if I'll have 1, I can predict, right? If I'll have 1, then I can predict. Whenever I have 1, I can predict the output, but if I'll have 0 combination, then I cannot predict the output. So the conclusion is, whenever your outputs cannot be predictable in any type of logic circuits, if your output cannot be predictable, then you will have to consider, right? So you'll have to consider the fast states of the circuit. Fast states, see there, if your present state is qn plus 1 whole bar, then its past state is qn bar. If your present state is qn plus 1, then its past state is qn automatically, right? Now let's see there, whichever the value, I don't know actually what was there in the past. In the இடத்துல pastல என்ன value இருந்ததுன்னு தெரியல. So I'm just commonly considering there was a value is called qn. Either it may be 0 or 1, it does not matter. I don't want to know that one. Similarly, here we are considering qn bar. Let us consider qn bar here. Let us see the output now. See there, in one pin we are passing 0, in another one pin we are passing qn bar. So what will be our output now? Since it is acting as a NOR gate, in case of NOR gate, in the output, how we are receiving 0 plus qn bar whole bar. Correct? That is the output of the logic gate, that is a plus b whole bar. A plus b whole bar. Now according to De Morgan's law, it can be rewritten as a bar dot b bar. B is qn bar whole bar, such that double bar getting cancelled here, 0 bar will become 1, 1 into qn. So what is the conclusion? While passing 0 as the input of the first, right, for R, whenever while passing 0 as the input for this gate, your output of the qn plus 1 is going to be qn simply. Similarly, if we pass qn through this gate, it will become what? 0 plus qn whole bar. According to De Morgan's law, once again this is going to be 0 bar dot qn bar, such that 0 bar will become 1, qn bar will become once again qn bar only. That is how we are predicting the output whenever your outputs are, that is output of the logic gates are not predictable exactly in case of sequential circuit. Now let us proceed with the second combo, that is 0 1. Now we can happily predict the outputs. Let us see what happens now. Now when we are going up with the 0 1 combination, anyway for 0 our output is unpredictable. For 0 your output is unpredictable, but for 1 we can predict. Just now I told you, whenever we are having NOR gate, right, with your hand, that is in your hand, just observe the inputs of the NOR gate. If you find at least one 1, that is at least 1 1 in the input side, right, then automatically you can set the output as 0. See there, here I am having at least 1 value, right, such that automatically output of this NOR gate is going to be 0. Anyway, output of this NOR gate is going to be in the feedback line, it will reach the input of the second NOR gate, such that 0 0 will give you what? Again we are discussing about NOR gate only. Whenever we are passing 0 0 through the NOR gate, output of the NOR gate will become 1. So it clearly denotes, while passing 0 1 has the input for this NOR latch, our outputs are going to be, see there, qn plus 1 stands, that is 1, this is going to be 0. Let's continue our journey. Similarly, whenever we are passing, while passing 1 0, let's check the output. Now what we are going to get, see once again 0 output is unpredictable, but for 1 output is predictable, because whenever we are passing 1 through the NOR gate, automatically output of the NOR gate is going to be 0. So while passing 1, irrespective of another things, I can directly set the output of this NOR gate is going to be 0. Now output of the first NOR gate will act as a feedback for the second NOR gate, so automatically you can receive this 0 here. So if you pass 0 0 through the NOR gate, 0 0 output will become 1, such that while passing 1 0 has the input for the NOR gate, your outputs are going to be, for qn plus 1 we are receiving 0, for qn plus 1 bar we are receiving 1. Now we have to pass 1 1 immediately, but the beauty of this case is, the last case is, see I only told you for your NOR gate, right, there are 1000, you may have 1000 number of, that is thousands of inputs. If you find at least one input with the value 1, automatically your output of the NOR gate is going to be 0 only. From that conclusion, see there, this NOR gate also having the input as 1, automatically if you observe the another NOR gate, that is also having it input value as 1, such that first NOR gate output will be 0, automatically second NOR gate output also will going to be 0. But the thing is, if you observe these two guys, this is qn plus 1, this is qn plus 1 bar, it means these two people are always complement of each other. So what is the conclusion? If you are getting 0 here, definitely you have to get 1 here. Suppose if you are getting 1 here, definitely you will have to get 0 here, because these two outputs are always complement of each other. You cannot consider same value in both of these places. Why? Because then your statements will become what? Your postulates will be failed. Why? Because according to the complementary theorem, if I'll have 0 here, I must keep 1 here. If I'll have 1 here, I must keep 0 here. But here I'm not getting those type of combination. So the output of this state is called invalid state, or we can simply call it as don't care. Right? Anyway, this state is called invalid state or don't care. We can simply call them as invalid state or don't care. Now the second state, see there, let us go ahead. The first state is called Qn. Actually, while passing 0 0 has the input for this NOR type of latches, in the output side, see there, while passing 0 0, present output of the system is simply follows the past. This state is called holding state. It means whenever your inputs of the latches, NOR type of latches are going to be 0 0, whenever your inputs of the NOR type of latches are going to be 0 0, your output of the latches simply follows the previous state, that is called holding state, or we can also called memory, we can also called memory, right? So or we can also called stable state. We are not changing that state now, so it is simply called memory. It is simply called memory, or we are also calling it as hold state. Now the next thing, listen guys, see there, whenever, right, in this case, whenever your input, this is called set pin, whenever set pin value is going to be high, this is called high active input. Whenever your input line is going to be, see there, right, through S, whenever we are passing 1, automatically your output of the function will going to be set at a value of 1. Now remember, according to the positive logic, that is positive logic of the binary system, right, many of you guys are having a doubt with the negative logic systems. I will talk about negative logic system in logic families. Positive logic system means whichever the functions that we have gone through till now, they are simply called positive logic only. You don't need to separately think about the positive logic. Till now, whichever the things that we had discussed in digital, they are all called what? Positive logic only, right? So simply let me call it as positive logic. So in positive logic, high pin denotes set, low pin denotes reset. Low pin means 0, 0 denotes reset. According to this logic, I can say if your input for this set pin, whenever your set pin is going to be high active input, automatically output will be set as 1. Whenever your input high active, this is according to reset. Whenever in this reset pin, we are considering 1 as the input, automatically your output is going to be reset. So what is the conclusion? This pin is always called set pin. This pin is always called reset pin. If you want to set the output, listen guys, if you want to set the output as 1, if you want to set the output, then you have to pass the input 1 here. From these two combination, 1 you will have to pass here. If you want to reset the output, automatically you will have to pass 1 here. That is the conclusion. That is the why. That's why this terminal, this line is called set line. This line is called reset line. Clear? So immediately this one is called set, I can say, and this person is called reset. This person is called reset. So finally we have understood this is the basic truth table of your latches, right? So let me place them in a side, right? You please note down by yourself. Let me place it here. RS Q1 plus 1. So we are getting 0 0 0 1 1 0 1 1 this one will give us Q1, this one will give us 1, this one will be 0, this one will become invalid state, or we can call it as don't care. This is the truth table of what I can say NOR type of latch. Now we are going to design NAND type of latch, right? So let us complete this one. So let me rub this one. Let us design NAND gates based latches. Okay, let us design NAND based logic gates, right? So once again we are going to design the latches with the help of NAND gate, right? So let us do the same thing with the help of NAND gate. Now once again we are going to use cross coupled NAND gates only. There is no changes. Cross coupled NAND gates. Let us perform the operation with the cross coupled NAND gates, right? And once again this is going to be our output Qn plus 1, and let me simply call this one as Qn plus 1 bar, right? Now let us see the truth table. Let us realize the truth table of this NAND gate, right? So according to this NAND gate logic, first of all we need to realize the truth table of the NAND gate in order to perform this operation. Once again in NAND gate we have 2 input pins and 1 output pin, such that I can say input pin A, B and output pin Y. Now there are 4 possible combinations 0 0 0 1 1 0 1 1, such that, right, for NAND gate we all know the output. This is 1, rest of all wait a minute, this is 1, this is 1, last pin is going to be 0. Now what it stands in case of NAND gate, in order to set the output value as 1, at least one input value should be 0. At least one input value should be 0. In order to set the output value as 1, at least one input pin value should be 0. That is the basic logic begin of the NAND gate, right? So with this realization, let's start our journey with the latches, right? So once again in latches we are going to consider here, let me name them S bar. This is going to be R bar. This is S bar, and second thing we are going to consider R bar, and next in the output side we are going to get Qn plus 1, and this is going to be Qn plus 1 bar. Clear? Now so let us close this circuit. Now let me close them right together. Yeah, let's see, there are 4 combinations 0 0 0 1 1 0 1 1. Totally we have 4 possible combinations. Let us see its corresponding possible outputs, right? Now whenever we are passing 0 0, what will happen? I only told you in case of NAND gate, right, if I'll find at least one input pin as 0. See, in case of NAND gate you can consider thousands of inputs, thousands and thousands of input, right? If at least one input pin value as 0, automatically we can say it output is going to be 1 only. Irrespective of other input lines, if at least one input line is 0, automatically output line is going to be 0 in case of what? NAND system, that is NAND logic gate, right? According to this conclusion, let's take our system. If I'll pass 0, automatically output will become 1. If I'll pass 0, automatically output will become 1. Now see there, I only told you in your output side always Qn plus 1 and Qn plus 1 bar will always complement of each other, but here see there both states are going to be 1. So once again this state is called invalid state, or we are calling it as don't care. Both are getting 1, right? So is it possible? No, right? So this state is simply called invalid state. Let us call them as invalid state. Okay, now let us see in the rest of cases. If I pass 0 1, see that if I pass 0 and I will pass 1 here, see for 0 we can predict the output, with the 1 I cannot do anything, right? I told you with the 0 we can guess the output of the NAND gate. So if I pass 0, automatically I can say the output of the function is going to be 1. If I pass 0, output is going to be 1. Now this 1 we can receive through the feedback line to the second NAND. Now 1 1, right? For the NAND gate, if I pass 1 1, output is going to be 0. So what we have understood, if I pass 0 1 as the input for the NAND gate, output is going to be 1 0. Okay, if I pass 1 0, what will happen? With the 1 I cannot do anything, but if I pass 0 I can predict. See there, if I pass 0, automatically output of the NAND gate is going to be 1. At least one input must be 0 in order to get output as 1, right? So if it is 1, automatically through the feedback line we can receive 1 here. See there, while passing 1 1 through the NAND gate, output is going to be 0. So I can say output is 0. So see there, while passing 1 0 has the input for your NAND gate type of, that is NAND based latches, your output is going to be Qn plus 1 is 0, Qn plus 1 bar is 1. Now when I am passing both are as 1, can you predict the output? No. The problem with this one is, if I have 0, then I can predict the output. But if both are 1, you are unable to predict the output. So whenever you are unable to predict the output, just consider the fast data, Qn and Qn bar. Right? If it is Qn through the feedback line, it will come here. If it is Qn bar through the feedback line, it will come here. So automatically, right now, let us see the output of this NAND gate. The output of the NAND gate is going to be 1 dot Qn bar whole bar, according to, that is basic logic of the NAND, A dot B whole bar. Now, if I will apply De Morgan's theorem, it will become what? 1 bar plus Qn bar whole bar, such that double bar getting cancelled. Anyway, 1 bar will be 0, 0 plus Qn should be equal to Qn only. So what I got, for Qn plus 1, we are receiving Qn. Then in the opposite case, what we are going to receive? See there, I am receiving Qn here, Qn dot 1 whole bar. Qn dot 1 whole bar is nothing but what? Qn bar only, such that it is going to be Qn bar. So we have realized NAND based latches also. Clear? So the drawback is, now I understood one thing. Listen guys, with the help of, see there, now coming back to the realization. So what we have understood here, see there, whenever your inputs are going to be 0 0, automatically your output is going to be what? In case of NAND based latches, if your inputs are 0 0, then output state is going to be invalid state. Now if your input is 0 1, if your inputs are 0 1, then we are setting, your output is going to be, your value is set, right? Your value is going to be set. If your input is 1 0, then your output is going to be, this is called reset. If your value is 1 1, then this is called holding state, or we can call it as memory. We can call it as memory. Clear? But the conclusion is here, see there, why I am putting S bar and R bar here. See, S bar denotes, first of all, this bar denotes, we are considering active low as the input. Active low input. We are considering active low input. Active low input, it clearly indicates we are treating 0 as the active low input. See, whenever in the set line, if it is going to be 0, then your output will be set. In the reset line, if it is going to be, see there, when your reset line is going to be 0, then your output will be reset. See there, in your set, in the set input line, if you are setting your input line as 0, automatically output will be set. In the reset line, if you are setting the input line as 0, automatically output will become reset. But in order to, right, we are representing it in min-term form. So 0 will be represented as 0 bar, 0 will be represented as 0 bar. So we are just considering, in order to consider the reset and the set line. See, this is the most important consideration for us, because our target is we are trying to design the memory circuits. So in the output side, I will have to fix some values with the help of the variable input combinations, right? So with the help of reset and set pin, automatically I can set the value of the outputs. Either you can set the output value as 1, or you can set the output value as 0 permanently. That is called memory state. In order to set the memory state, in order to create the memory state, two input lines are very important for us. One is set line, another one is reset line. We are receiving those two lines with the help of these two bits. Anyway, the problem with the latches is, right, this is called uncontrollable circuit. This circuit is called uncontrollable circuit. Do you have any controlling here? No. In case of uncontrollable circuit, there is a big problem that is called error, right? There is a term is called error. Actually, what do we mean by error? It means, see there, suppose with the help of these latches, if I am designing some other type of sequential circuit, right? For an example, if I am designing some counter circuit, right? If there is any malfunctioning, right? If there is any malfunctioning in the circuit, in this circuit, right? There is no person to control that malfunctioning, or there is no person in order to detect the error, or there is no person in order to improve the accuracy of the system. So the problem with the latches is, if there is any malfunctioning in the output coding, automatically output of the system will be changed. So in order to overcome the error issue in case of latches, we are immediately moving on to the next type of circuit, that is called flip-flop, right? So let us take the second type of circuit, that is simply called flip-flops. So anyway, we are going to design the flip-flops with the help of basic latches only. Don't think that the flip-flop is separate version. Flip-flop is the special or advanced or modified version of the latches only. The problem with the latches is there is no controllable circuit. So we are attaching one more circuit with this latches, such that the circuit will become what? Latches plus controllable circuit automatically. In order to, because of bringing the controllable element into the circuit, just we are controlling this output with the help of a controller, right? So we are going to remodify the circuit, that is simply called flip-flop, right? So in your flip-flop, what is the purpose? Your flip-flop will going to synchronize the output, right, it is going to synchronize the output. At the same time, see, usually we are facing this error in case of latches. It's due to delay of your gates. Usually your NAND gates and NOR gates are providing some type of delay that is simply called propagation delay. That propagation delay will be controlled such that your input and outputs are going to be synchronized with the help of a synchronized clock pulse. Right, so in order to synchronize the input and output, and in order to avoid the delays, right, in between the output and the inputs, right, we are moving on to the next type of circuit, that is the modified version of the latches, that is simply called flip-flops. Right, so let us take the flip-flop and let us design the flip-flop circuit, right, one by one. So basically we are going to design 4 types of flip-flops. Right, one is SR flip-flop, and the second we are going to design JK flip-flop, and then we are going to design D flip-flop, and then we are going to design T flip-flop. Right, so totally we are going to design 4 type of flip-flops. Right, so there are some drawbacks in some flip-flops, right, that flip-flops drawbacks will be overcome by the other flip-flops. Right, we will see all those things one by one. First I would like to design SR flip-flop. Right, so let us design the SR flip-flop. Right, so let us design SR flip-flop. So slightly I am modifying the circuits that we saw in our last class just to forget that things. Right, let's start from the beginning. Right, so the thing is in SR flip-flop, right, so first we are going to consider once again, listen, in order to design the flip-flop circuit, right, either you can consider AND plus NOR gate combination, or you can consider NAND plus NAND gate combination. These are all the 2 pair of the logic gates that we are going to consider in order to design the flip-flops. Either you can go up with this combo, or you can go up with this combo in order to design the latches, in order to design the flip-flops of the circuit. Right, so anyway, I would like to design this SR flip-flop with the help of NOR gate. Right, already we have the NOR gate truth table, that is NOR latches truth table here. So let me take the latches first and let me show you how we are bringing the modified version. Right, so the modified version is going to be, let me close these 2 circuits first. Right, let me close them. Right, once again we are considering latches only. First we will consider latches, and then we will modify the circuit. This is cross coupled NOR gates. Right, and there are 2 input lines. Right, so for this, now these 2 input lines are going to be controlled with the help of, see there, NOR plus AND will act as a flip-flop. So here I am using NOR gate. With this I am attaching one more circuit, that is called AND gate. Now in this AND gate, 2 input lines are going to be synchronized with the help of clock pulse. Here I am setting this clock value as 1, fixed, high value. Right, whereas there are 2 more input lines in this NAND gate. Here only we are going to provide the input. Right, so in this case what I am going to do, let us take this is our latches. Whereas in the output of the latches we are going to get Qn plus 1, and this is going to be Qn plus 1 bar. Guys, I am slightly modifying the circuits because I said there are many ways to design the flip-flops. Right, so earlier I was going up with the 4 and 5 methods separately. That's why yesterday while designing this flip-flop I made separate method, that is I just went up with the separate method. Again while moving on to the JK flip-flop I went up with the separate method. Later only I realized that mistake. Right, because of that only there was a error. Actually that was simple mistake only, but we cannot go through that way. So again I had remodified the circuit. Let's proceed with this one. Right, see there, here in this case what I am going to do, let us see, nothing is there. This is SR latch, and we all know this is called R and this is called S. Same thing just to consider here. Here also I am going to consider R, here also I am going to consider S only. Let's see. The thing is, now we have to design the truth table for this circuit. So first step we have to realize the logic gates. Right, second step we have to design the truth table. So first we are going to design SR flip-flop. I said we are going to design 4 type of flip-flop: SR flip-flop, JK flip-flop, D flip-flop, T flip-flop. Right, so in order to design the circuits, either you can go up with the NAND logic, or you can go up with the AND NOR logic. Right, so here I am just going up with the AND NOR logic. Right, okay, fine. So let us try and figure out the answer for these functions. Anyway, the inputs are going to be R and S. Right, so we are considering R and S as the input. Right, so with this we are going to predict the nature of the output here. Right, so the nature of the output is, so hereafter I don't want to consider the complement of this Qn plus 1, because we know now we know how we are going to get the outputs. Right, so simply I will consider 3 columns here. So we are going to consider 4 possible inputs. We all know they are simply called 0 0, 0 1 and 1 0 1 1. At last we are going to consider 1 1. So let's try and figure out the answer for this function. Now whenever we are passing, just to keep your attention here, we know the truth table of latches. This is latches. So latches plus AND gate, it's simply acting as a SR flip-flop. right? Okay, let's see. The thing is, whenever we are passing 0 0 has the input. First of all, in order to realize the circuit, this is very simple AND gate, right? So let us take the AND gate circuit. First of all, in AND gate we have two inputs and one output. For AND gate I am writing the truth table. While passing 0 0 0 1 1 0 1 1 has the input combinations, we all know in AND gate for 0 0 we are getting 0 0 0, for 1 1 only we are going to get the output. If you observe the AND gate, right, if you realize the AND gate carefully, if I will find any at least one input as 0, automatically output is going to be 0. If at least one input line will be 0, automatically AND gate output is going to be 0. It means you can consider 1000 input lines, right? With in case of AND gate, if I find these 1000 input lines are not known, but there is only one input line that will be connected with 0, automatically output of the AND gate will be going to be 0 only. So the conclusion is, whenever we are getting 0 0, we can easily predict, right? If I have 0, then I can guess the output of the AND gate, right? So let's conclusion. See that. Let us coming back. This is clock, right? So there are two input line for your AND gate. One is 1 line is fixed, whereas another line are going to be inputs, right? They are in our control. Let's see, whenever we are passing 0 0, now what will happen? This 0 will enter here, this 0 will enter here, such that 0 into 1, here also 0 into 1 will going to give you what? 0. Because 0 into 1 will always be 0 in the output line. See there, if both are 0 0, see there, immediately 0 and 0 will enter into the latches. Now, whenever we are passing 0 0 into the latches, whenever we are passing R, through R we are passing 0, through S we are passing 0. Whenever we are passing 0 0 through the latches, what will happen? Output of the latches are going to be QN. Same circuit will happen here, since it is acting as a latches only, but with the somewhat controllable circuit. So such that I can say, while passing 0 0, immediately when this 0 0 will enter into the latches, output will become what? QN only. There is no changes. Now let us consider the second target, right? Suppose if it is going to be 0 1, is this visible to you all? Let me, yeah, that is visible only. Nice. So whenever we are passing 0 1, let's see what will happen. See there, if I will pass 0 1 through the circuit, this 0 will enter here, this 1 will enter here, such that 1 into 0 is going to be 0, 1 into 1 is going to be 1. See there, through the latches, if I will pass 0 1 has the input, 0 1 has the input, output of the latches automatically will become 1. Now let us consider the next case. 1, this is going to be 0. If I pass 1 0 has the input, let's see what happens. If I pass 1 and 0 has the input, see there, 1 into 1 will give you 1, right? And 0 into 1 will give you 0. What will be the conclusion? If I pass 1 0 has the input for your latches, 1 0 has the input for your latches, output of the circuit immediately going to be 0. Now when we are passing 1 1, let's see, 1 into 1 will give you 1, 1 into 1 will give you 1 only, such that 1 1 has going to be the inputs for your latches. Whenever we are passing 1 1 through the latches, output state is simply called invalid state, or we can simply put don't care. This state is called what? Invalid state. This state is called what? Invalid state. Now, if you observe this state once again, see there, whenever your set pin is going to be whenever your set pin is going to be high, automatically output is what? Setting its state. Whenever your reset pin is going to be 1, automatically output is what? That is reset. Its state is what? Reset. Similarly, see there, 0 0, that is called what? Holding state or memory state. This is hold or memory state. Right, this is hold or memory state. Okay, so this is simply called SR flip-flop. So what we have done in SR flip-flop, the first thing is we have to realize this circuit. Yes, we are realizing. Second step, we have to design the truth table. Of course, we were design. Now, in case of flip-flop circuits, right, we are going to consider there are continuously we are going to do 5 operations. Step number 1, we have to realize the circuit. Step number 2, we have to design the truth table. Step number 3, we have to design the characteristic table in order to guess the characteristics of this person, right? Step number 4, we have to form the characteristic equation. Step number 5, we have to write down the excitation table. Step number 7, we are going to design the state diagram for this circuit. Of course, while telling these things, it might be there are big data, but while developing these things, they are become chilly only, right? Let's see, this is the truth table of the SR flip-flop. Up to now, I hope there was no doubt, right? So immediately after developing the truth table for your SR flip-flop, your immediate task is we will have to design the characteristic table for the SR flip-flop, right? So let us design the characteristic table for the SR flip-flop, right? So for that one, let me remove this one, right? So let us remove this one. Let us bring the characteristic table for the SR flip-flop. Yeah. Now, see, the thing is what do we mean by characteristics? if you want to guess the characteristics of the person, you have to know the present status that you are going to put on him, as well as we have to know the past data. For an example, you are a new student for me. Right now your parents are asking me in order to train you. Now what I have to do, first I have to observe your characteristics in the past, what you have done, right? In the semesters, right? What was your percentage and how was your, that is your skill, your ability, and how you are catching the things while teaching. Everything I will have to analyze. For that it may take some time for me. That is called past data. Just I am collecting the data. That is called past, right? So I am in need of past output. In past, right, whichever the exams that you have written, I have to guess, right? With the help of those outputs, I will have to guess your characteristics, right? And then I will have to, based on that, I have to put some present input, right? Now with this present input and past output, we are going to realize the future of the system. That is the present output of the system. With the help of the present input and past output, we are going to realize the present output of the system. That is in present how we are going to work, right? So I'm just guessing that one with the help of two people. One is your past output, right? Whichever the exams that you have gone through till now, I'm just taking that one. At the same time, I'm going to give some present input. So with the help of this present input and past outputs, I'm going to predict your nature, right? So now this is your current status. In future, this is the way you are going to be. So in order to predict that one, we are going to do some things that is called a characteristic table in flip-flop circuit. So let us design the characteristic table of the flip-flop circuit. So I said in order to design the characteristic table, we need two people. One is your present input, that is called simply RS. In case of flip-flop, that is in SR flip-flop, our present inputs are R and S, whereas output, that is past output, simply called Qn. Whenever we are treating Qn plus 1 as the present input, then automatically Qn is going to be the past output. See, Qn plus 1 is going to be the present output. Sorry, Qn plus 1 is going to be the present output. Whenever we are treating the present output as Qn plus 1, immediately Qn is going to be the past output. If it is present output, it is going to be past output. Clear? So let us see. So this is past output, this is present inputs. Let us guess the present output of the system. The present output is simply called Qn plus 1. Clear? Let us see. See there. Now I have to realize the circuit possibilities. Let us see how to realize these things. See there, first when I am giving your input as 0 0 for your R and S, if I am giving 0 0, your past output of the system might be 0, or while giving 0 0, your past output of the system might be 1. Now while passing 0 1 has the input, your past output might be 0, or while passing 0 1 has the input, your past output might be 1. Let's consider, or your present output, when I am giving 1 0 as the present output, your past output might be 0, or while passing 1 0, your past output might be 1. Now when your present input is going to be 1 1, past output might be 0, or while giving present input as 1 1, past output might going to be 1. Clear? So with this, let us consider the output, that is characteristic table of the system. This is called characteristic table. Now in order to realize the output of the characteristic table, so let me just put the title here, that is going to be characteristic table. That is simply called characteristic table. So I am just simply calling it as characteristic table. Let us see the output of this characteristics table. Guys, listen. See, the characteristics of the person is going to be guessed with the help of past and present input, past output and present input. Let's start our journey. See, whenever we are passing 0 0 has the input, whenever we are passing 0 0 has the input, present output of the system is simply follows Qn. See there, we are realizing characteristic table from truth table only, right? So first step, we have to design the truth table. Now from truth table, we have to realize the characteristic table. Let's realize. See there, in this truth table, whenever we are passing 0 0 has the input for our SR latch, your output present, Qn plus 1 denotes present only, na? So this present, it simply follows Qn. Qn is what? Hold or past state, right? So this is Qn. So it means while passing 0 0, whichever the data that we are having in the past, same data will become present. That is the meaning of this one. So while passing 0 0 has the input, whichever the data that you are having in the past, that is going to be the present. Next one, while passing 0 1, see there, while passing 0 1 has the input for your SR flip-flop, it clearly indicates its output is going to be, present output is going to be 1. It means while passing 0 1 has the input, your output of the system, this is present output of the system, irrespective of the past responses, it is simply set its value as 1, such that irrespective of the past, whenever we are passing 0 1 has the input, output is permanently fixed as 1. See that 0 1 0 1 in both cases output is going to be 1 1. In this case it won't care about the past values because it is permanently fixing its value. So that is the beauty of your system. We are designing the memory, right? So while passing 1 0 as the input, irrespective of its past response, its present is going to be reset such that irrespective of while passing 1 0 irrespective of the past, present is going to be 0 0. Now while passing 1 1, output state will become invalid state. That is, we are simply, some people are calling it as just we are putting some bar, and we can also put some don't care. That is not known, because in digital we have only two values, either it might be 0 or it might be 1. Invalid state in the sense, in that invalid state either you may have 0 or you may have 1, but that is not exact value, that I know. That's why I'm putting what? Don't care. It's over. Now second step, we have to design the characteristics table. That is over. First step, we have to realize the truth table. That is also over. Now step number 3. Okay, this characteristic table, this truth table, I'm going to use it in future. For that I'm just putting in this side. So this is what we are getting: R S Qn plus 1, and we are realizing 0 0 0 1 1 0 1 1. Its present outputs are Qn. This is 1. I think that is 0. This is going to be don't care. Clear? That is the truth table of SR flip-flop. Just let me put it in a side. In future I am going to use that one, right? Fine. Let's see. Now immediately, first with the help of truth table we are realizing the characteristic table. Now with the help of characteristic table we have to realize two things. One is characteristic equation of the system, and second one is excitation table, right? So next we have to design. First we are going to write the characteristic equation, right? So we are going to write characteristic equation of the system. Yeah. So let me do it. So the first thing we are going to realize characteristic equation. So the next one is characteristic equation. Okay, so let us bring that one. In order to bring the characteristic equation, see there I have 8 variables in the output, right? So in order to get the exact answer, let me put them into the K map. So let us put them into the K map, right? So here we need 8 adjacent, that is 8 cells, in order to bring out the answer, such that R, let me consider R here, let me place R bar R. We are writing the answer in min term, that is SOP form, sum of products, and then here we are going to consider S bar Qn bar, that is present inputs past output. S bar Qn bar, this is going to be S bar Qn, this is going to be S Qn, this is going to be S Qn bar. Let us register the variables into the correspondent blocks. See, for the first 0, I have 0, 1, 2, and then 3, and then 4, 5, 6, 7. Let us club them in order to find out the answer. See there, if I'll club these 4 variables together, your output of the system, that is called Qn plus 1, characteristic equation of the system, can be simply written as, see there, in these 4 terms, R plus R bar is going to be 1, whereas here the common variable is simply going to be S, I hope, plus. The second case, there is one more grouping. If I'll group this one, here it is going to be immediately R bar into the common term between these two person is going to be Qn. So this is the characteristic equation of your SR flip-flop. Clear? So let me put that one also here. So I am getting S plus R bar Qn. In future I am just I'm in need of these things. Okay, fine. So this is the characteristic equation. So immediately after designing the characteristic equation, our next task is we have to design the excitation table, right? So excitation table, first of all, what do we mean by excitation table? Excitation table in the sense, we know the past output, we also know the present output. So with the help of the past and present outputs, we are guessing the inputs of the system. Inputs வந்து எந்தெந்த மாதிரிலாம் இருந்திருக்கலாம் அப்படிங்கறத நம்ம கெஸ் பண்ணி பார்க்கறோம், right? So it's very simple. If you are taking the solar system, our sunல நம்ம என்ன பண்ணிட்டு இருக்கோம்? இப்போ வந்து presentல வந்து அது எவ்வளவு எனர்ஜி டெலிவரி பண்ணிட்டு இருக்கு. Pastல வந்து எவ்வளவு எனர்ஜி டெலிவரி பண்ணிருக்கலாம். அதை வச்சு நம்ம என்ன பண்ணிருக்கோம்? Just we are telling that இந்த யூனிவர்ஸ் வந்து எப்போ வந்து உருவாகி இருக்கலாம், எந்த டைம்ல வந்து இதோட ஆரிஜின் வந்து ஸ்டார்ட் ஆயிருக்கலாம், இந்த எர்த் வந்து எப்போ வந்து எக்ஸிஸ்ட் ஆச்சு, எப்போ first வந்து இதோட ஆரிஜின் வந்து ஸ்டார்ட் ஆச்சு. Everything we are guessing. How it is possible? With the help of present and past characteristics. That's all. It's over. Clear? So that is what we are going to do now. So with the help of the present outputs and past outputs, we are going to guess the inputs of the system. Inputs இந்த மாதிரிலாம் இருந்திருக்கலாம், right? Whichever the possibilities that we are having, that we are going to bring it out. That is called excitation table, right? So immediately we are going to design the next one, that is called excitation table, right? Yeah, let me remove this one. Let us design the excitation table, right? So next we are going to design excitation table, right? So keep the heading. We are going to design excitation table. First of all, from the logic circuit, we had been realized the truth table. From the truth table, we are realizing characteristic table. From the characteristic table, we are realizing excitation table. Next one, right? So anyway, in excitation table, I told you consider past output and present output. With this, we are going to guess the outputs of the SR flip-flop, right? So let us see how to design this one, right? Either you can consider RS or SR here. Just I'm in need of the table, that's enough, right? It is excitation table. It is simply called excitation. So if we are going to consider 0 0 0 1 1 0 1 1, these are all the going to be possible outputs, right? So with this, let us see. Now see there, when your input present, when your past output is 0 and present output is 0, rendu perume present past, right? So see the past output, present output rendu perume 0 இருக்கும்போது its correspondent possible inputs are, let's see there, present 0, sorry, past 0, present output 0 இருக்கு, கரெக்ட்டா? Is there any other combo? Yes, இங்க இருக்கு பாருங்க, கவனிங்க. past output 0, present output 0, past output 0, present output 0. அப்ப இந்த மாதிரி இருக்கும்போது its correspondent possible inputs are, let us check, its correspondent possible inputs are 0 0 and here it is 1 2 3 4 5 1 2 3 4 5. Let us take this one. What we have understood, listen here, when your present output and past output are going to be 0 0, under that condition its possible inputs are, input la pathinga appadina, see there, in the set pin your value is always 0, whereas in the reset pin we have 0 and 1. There are two possibilities for reset pin. So for the reset pin we are going to put don't care, whereas for the set pin permanently this value is fixed as 0. See guys, listen, don't care denotes either that value might be 0 or 1, but set pin is 0. See there, set pin value is fixed, whereas don't reset pin value either it might be 0 or 1. There are two possibilities, so I cannot directly consider 0 or 1, right? So directly let me put don't care. Don't care denotes either 0 or 1. Clear? That's all. Let's proceed with the 0 1. How many possible outputs are there? 0 1, we have only one possibility, 1 2 3 in the third place. See there, in the third place, see there, past 0, present 1, past 0, present 1. Its possible inputs are 0 1 only. For R we are going to consider 0, for R we are going to consider 0, and whereas for S we are going to consider 1. Clear? So let us consider next possible inputs are 1 0. See, present is 0, past is 1. Present is 0, so let us consider present is 0, past is 1. Let us consider this one. Present is 0, past is 1. Present is 0, past is 1. Its possible inputs are correspondent 1 and 0, because only one possibility, 1 and 0. For reset pin we are considering 1, for set pin we are considering 0. Let us consider the last case, that is 1 1. How many possibilities are there? Here we have the possibilities, this one 1 1, and we have one more possibility, this one 1 1, such that if you observe its correspondent inputs, they are going to be, see there, this is 0, here also we have 0, this is 0 or might be 1. See there, did you understand? In the reset pin we have this is always 0, whereas in the set pin it might be 0 or 1. So it is simply called don't care, right? So in the set pin we are simply called don't care, because either it might be 0 or 1, whereas in the reset pin we are fixing this value as 0. Clear? We are fixing this value as 0. It's over now. Clear? So let's continue. This is simply called the excitation table, right? So immediately after designing the excitation table, our next task is we have to design the state diagram, right? So let us design the state diagram also. So let me rub this one, because characteristic table over. Now we have designed excitation table also. Our final step is we have to design state diagram of the circuit. So let us design the state diagram. So finally we have to design state diagram, right? So let me do that one also. Now how we are going to design state diagram? Okay, fine. How will you design the state diagram? First of all, listen guys, state diagram அப்படிங்கிறதோ in state diagram there are two possibilities. You may have 0 as the output, or you may have 1 as the output. Listen guys, யூஸ்வலாக வந்து நம்ம எத்தனை அவுட்புட்ஸ் கன்சிடர் பண்ணுறோம்? பாஸ்ட் அவுட்புட், ப்ரெசென்ட் அவுட்புட், ரெண்டு கேசஸ் வந்து யூஸ்வலாக கன்சிடர் பண்ணுவோம். அண்ட் செகண்ட் திங்க் இஸ், இங்கே எத்தனை பிட்ஸ் வந்து நம்ம கன்சிடர் பண்ண போகிறோம்? எதர் 0 மட்டும் நம்ம கன்சிடர் பண்ணுமா, இல்லை 0 0 1 1 கன்சிடர் பண்ணுமா, இல்லை 0 0 0 1 1 0 1 1 கன்சிடர் பண்ணுமா? இட் டிபெண்ட்ஸ் ஆன் தி நம்பர் ஆஃப் flip-flop that we are choosing. Anyway, in this case we are traveling along with only one flip-flop, that is simply called SR flip-flop, right? So if you have only one flip-flop, then in the output side you can consider single bits, right? In that single bit, just just consider 2 bits. Either it might be 0 or it might be 1 possibilities, right? Output 0 or 1 or, but here we are going to consider 2 possibilities. You have to consider the past output, you will have to consider the present output. Anyway, state diagram will be implemented from the excitation table. That is the sequence. First we took the logic gates and then we designed truth table, right? From the logic gate, from truth table we are realizing characteristic table, from characteristic table we are realizing characteristic equation and excitation table, from excitation table we are designing the state diagram. Just to follow this sequence, don't follow any other procedures. I told you there are many other methods. First of all, directly we can design the excitation table from after understanding the truth table. That is another way of approach, but that will confuse. I don't think that is helpful to you all. Just go ahead with this procedure. Definitely it will help you, because if you find any different circuit, there also you can go with the same approach and you can predict the answers, right? Fine. Let me proceed with this one. In state diagram, what I am going to do, see there, past is 0, present also becomes 0. Whenever your past is 0 and present also will become 0, its correspondent possible inputs are 0 by x. So let me write like this. See there, past is 0, present also will become 0. Whenever past is 0, right, and then we are giving our inputs, right, we are giving 0 by x as the input. While giving 0 by x as the input, present also will become 0. It means we are starting from here, we are ending here itself with the 0x as the inputs. Again, past is 0, present will become 1. See that past is 0, present will become 1. Again, past is 0, present will become 1. With this, its correspondent possible inputs are, for S we are giving 1, for R we are giving 0. The next case 1 0. See there, 1 0 in the sense, see there, past is 1, present is 0. Past is 1, present is 0. Its possible inputs are, for S we are giving 0, for R we are giving 1. Whenever we are giving 1 0 as the input combo, this one, while giving 0 1 as the input combo, immediately your present and past relation is going to be like this. Now, whenever your past is 1, Qn denotes past, Qn plus 1 denotes present. Past is 1, immediately we are getting back to the same state, but its correspondent possible inputs are, for S we are giving x, for R we are giving 0. This is how we are designing the state diagram for the given circuit. I hope things are very clear to you all, right? So let's proceed with the next type of flip-flop. This is all about, wait a minute. Yeah, so this is all about SR flip-flop, right? So our next task is immediately we have to design JK flip-flop, right? So let us realize JK flip-flop, right? So let me remove this thing, that is let us rub these things. So now we are going to design JK flip-flop, right? So let us realize the properties of JK flip-flop with the help of SR flip-flop. Okay guys, listen, I told you in yesterday also I have done the same thing, but I said I took second model, right? There is one more model, right? So I have gone through. In SR I went up with the first model, in JK I went up with the second model. That's why there was a collapsion, right? Fine, let's coming back. In order to design the JK flip-flop, right, I said you can bring the relation between, first with the help of SR flip-flop we can design JK flip-flop, D flip-flop, T flip-flop. Again with the help of JK flip-flop we can design SR flip-flop, D flip-flop, T flip-flop. Again with the help of D flip-flop we can design T flip-flop, SR flip-flop, JK flip-flop. Again with the help of T flip-flop we can design D flip-flop, JK flip-flop, SR flip-flop. So the conclusion is you can bring any flip-flop from any flip-flop. That's all. That is the conclusion. Now in order to realize these circuits in a simplest way, I would like to go up with the conversion method, right? So we are realizing, we can realize, so I understood one thing, JK flip-flop can be realized from SR flip-flop. Do you all agree with me now? Yes, of course you will have to agree, because I can design any flip-flop from any flip-flop. That could be possible now. So in order to realize the circuit in a simplest way, I am just going with the conversion method. Later I will prove how it was possible. Clear? First I will take the circuit directly. Later I will just prove it. You don't need to be panicked, right? So proof will be given to you, and the demonstration you will be able to design any type of flip-flop from any type of flip-flop. If they will give you any general circuit also you can design, right? So let me demonstrate all those things one by one. Anyway, first our target is we are going to design JK flip-flop now, right? So let us take the JK flip-flop, right? So let us consider JK flip-flop. Okay, now I would like to design the JK flip-flop with the help of SR flip-flop only, right? Class is going good, yeah, I think class is going good. Okay, fine. Okay, let us design JK flip-flop, right? So what I had been done, see, let us consider this is going to be our JK flip-flop, right? So let us realize the JK flip-flop now, right? So first of all, here I am considering, actually this is SR flip-flop. Guys, listen. This is the simplest way of representation of your flip-flops. First of all, after designing the complete circuits, finally, generally your SR flip-flop will be represented like this. right? SR flip-flop, that circuit will be hidden back, right? In outside, the layer of the circuit will be, this is simply called S and this is called R, right? So that is actually we are considering RS, right? Either you can consider RS, it's up to S, it's up to S only, but now, because now we know all it's corresponding input lines, right? So this is going to be the outputs. Now we can simply consider, I said we are simply putting Qn and Qn bar here, because now I am not going to do any that is comparison in between past output, present output at all. This is simply a this is the representation of your flip-flop, that is the layout of your SR flip-flop, right? So let us coming back, let me take the layout of the SR flip-flop. So let us take the layout of the SR flip-flop. Now I am just considering S here, I'm just considering S here, and I'm just considering R here, right? So let's see, please don't make notes, right? Just observe here. Let's see what happened. Now here immediately once again here we are going to travel along with the Qn plus 1. I'm just talking about future inputs, guys. This is the realization representation of your circuit, forget about that one. Take the next circuit. Now we have to design JK flip-flop, right? So I'm just proceeding with the SR flip-flop with in the input side I'm bringing one more term that is called AND gate. Here also I'm bringing one more term that is called AND gate. Now in this AND gate I'm going to connect this one with the yeah, please wait a minute, let me connect this one with this one. Okay, that's fine. And here I'm taking one more line from here. Let us consider this one with this one, right? Yeah. So here the outputs are going to be what? Qn plus 1, and this is going to be Qn plus 1 complement of your input. Clear? So let us consider our inputs now. So let me consider J here and here. Don't note anything, just observe, first observe, right? Because you have to understand. The first thing is, let us realize the JK flip-flop output. JK and Qn plus 1 is going to be our output now. Let us realize, first step, we have to realize the truth table of this circuit, right? So let us realize the truth table. Once again, for JK, there are 4 combo, 0, 0, 0, 1, 1, 0, 1, 1. That is going to be the truth table. Let us design. See, first step, when your inputs are going to be 0, 0, when inputs are going to be 0, 0, since we are using AND gate here, since you are using AND gate here, see there, for your AND gate we have 4 possible combinations with output 0, 0, 0, 1, 1, 0, 1, 1. In AND gate, what we have realized, see there, whenever inputs are going to be, if you find at least one input pin as 0, automatically output is going to be 0. That is the output of that is the realization that we are getting from the AND gate. At least one pin input is 0, automatically output of the pin is going to be 0. See there, at least one pin input is 0, irrespective of another pins, automatically you can set the output of the AND gate as 0. See there, here I am putting 0, here also I am putting 0. Immediately output will become 0. In this case, you no need to be panic about the data that we are receiving in this line. You might be wonder, but that is not required, because in this another input line we are giving 0. Right? With the 0, whichever the information that we are going to collect, that will be what? Useless, because 0 will going to be multiplied with the data, automatically resultant will become 0 only. Okay, fine. See there, now we are passing this 0, 0 through the SR flip-flop. Whenever we are passing 0, 0 through the SR flip-flop, this is the truth table of the SR flip-flop that I have written it already here. Now see there, whenever we are passing, right, whenever we are passing 0, 0, right, through the SR flip-flop, output of the flip-flop will become what? Qn. So here output of the flip-flop will become Qn. See, here we are passing 0, 0. After crossing the AND gate, we are getting same 0, 0 only, such that now it is become SR flip-flop. If I will pass 0, 0 through the SR flip-flop, automatically output will become Qn only. Let us realize the second case. When I am putting 0, 1 here, see there, see second combination. This is 0, this is 1. Anyway, the conclusion is, if I will pass 0 here, immediately this 0, what will happen? See there, 0 will become 0 only. But if I pass 1 here, output of the AND gate is unpredictable. I only told you, if I will go with 0, I don't have any issues. But if I will go with 1, I will have the problem. Output of the gate is unpredictable. Let us see. In this case, let us take the output. Guys, listen. Here, in this pin, output is not known. In the other output, but here it is fixed. Because here we are passing 0, automatically it will become 0. Now, let us keep your target at this point. Let us keep a target at this point. Let's see. In this case, output is unpredictable. See, output of this AND gate is unpredictable. But one thing I understood, this output is hardly depend on the line information that we are going to get it here. Because here we are getting 1. If I unless, right, until knowing the information that we are going to get from here, I cannot guess the output. I have to know the input, that is, I have to know the information that I am going to get it from here. இங்க இருந்து உங்களுக்கு என்ன இன்ஃபர்மேஷன் வருது அப்படிங்கறது தெரிஞ்சா மட்டும் தான் இந்த பாயிண்ட்ல உங்களோட அவுட்புட்டை கெஸ் பண்ண முடியும். Are you agree with me? Yes. So here there are two possibilities. Anyway, the first possible combination is, this is the new circuit. Just let us assume this is new circuit. If it is new circuit, then here output is what? 0. There was no memory initially. That is the new state. If it is 0, then this 0 will come here, this 0 will come here, such that 0 will enter here. 1 into 0 immediately will become 0. Now through the SR flip-flop, whenever we are passing 0, 0, it output will become what? Previous state. Qn, see there, Qn plus 1 denotes Qn. Qn another hold state. இதுக்கு முன்னாடி நீங்க என்ன கன்சிடர் பண்ணீங்க? 0. Same state will be repeated once again. If your inputs are going to be 0, 0, previous state will be again what? Repeated. That is the meaning of this one. Suppose, let us consider the second state. Let us consider the second state. See there, I was assuming 0, I am getting what? Next state also becomes 0. Suppose, if I will consider 1 here, because I don't know, no? Either 0 is possible or you can also get what? 1 also possibility will be there. Suppose if it is 1, sir, that is old flip-flop. You said that is new flip-flop, because of that you took 0. Suppose I am having old flip-flop in my laboratory, then what will you do? That is what your case, right? So again I am putting 1 also possibility will be there. If I will pass 1 here, 1 will come here, 1 will come here, 1 will come here. Immediately 1 into 1 will give you 1 here. Now see there, for R we are putting 1, for R we are putting 1, for R we are putting 1, for S we are having 0, for S we are having 0. See there, for R, see there, for reset pin, for across the reset pin 1 is entering, across the set pin 0 is entering. Immediately what will be the output? Output is going to be, even if you are considering 1, output will become 0 only. Getting me? This is the point where I had a mistake in the yesterday class, because the problem is I was going up with another model, right? Okay, fine. Coming back. The conclusion is what? For reset pin we are passing 1. For reset pin we are passing 1. For set pin we are passing 0. Such that 0, 1, once again what will happen? 0, 1. In this combo, output of the SR flip-flop will become 0 only. Now, so what we have understood, either you can consider 0 here or you can consider 1 here. Irrespective of these things, present output once again going to be 0 only. So what will be the conclusion? While passing 0, 1 has the input for the JK flip-flop, your output is going to be 0. Permanently you can fix it now. Let us consider the another possibility. Suppose if it is become 1, if it is become 0, then what will happen? Let us see. Let us consider the another case. The conclusion is, in this case, I am passing 1 here, we are passing 0 here. Of course, that is true. But the thing is, if I have 0, immediately I can set the output, because AND gate. AND gate means whenever I am passing 0 through the AND gate, output will become 0 only. I don't have any issues with this. But when we are passing 1 through the gate, the problem is arises here. See, because output of the AND gate is unpredictable whenever we are passing 1 through the logic gate. So the conclusion is, in order to predict the output, I will have to go up with the what? Output of the system. Let's see. Suppose if I will have 0 here. If I will have 0 here, guys listen, if this input is 0, then opposite pin is complement of this one. If it is 0, then here you will have 1. That 1 will go here, that 1 will come here, that 1 will enter here. If I am assuming here it is 0, then opposite pin is what? Opposite pin is going to be the feedback for this one. If it is 0, then here you are going to get 1 only, that 1 will go here, that will enter here. So 1.1 will give you what? 1 only. Such that what will happen? Set pin is going to be 1. Yes, set pin is going to be 1. Reset pin is going to be 0. Just observe, set pin value is 1, reset pin value is 0. Such that output is what? 1 only. So what is the conclusion? Actually I was keeping 0 here, but in the next state I am getting 1. You may have, in the past state you may have 0, but while passing 1, 0, right, if it is 0, past state is 0, the present state will become what? 1 only. So suppose, opposite case, if it is 1, automatically here we are going to get 0. Now this 0 will come here, 0 will come here, 0 will come here, 0 will enter. If it is 0, 0 into 1 will become 0 only. Such that whenever you are passing 0, 0 through the SR latch, what it will do? While passing 0, 0 through the SR latch, it will simply hold the previous state. What is the previous state? I was assuming previous state is 1, so present state also going to be 1. What will be the conclusion? Either you can consider 0 or 1, output is fixed, that is 1 only. So what is the conclusion? That is 1 only. Happy now? Yes. So the next conclusion is, while passing 1, 1, let's see what happened, right? So when both are going to be 1, 1, that is the point where we have to realize the output, right? So let us target this one. Keep your attention here. Carefully observe me. Yeah. So let us consider. See, I said, if I have at least, if I have 1, 0, happily I can set the output of the AND gate as 0. Now see there, both are going to be 1, 1. Can you realize the output? Impossible. So what shall we do now? I have to realize the output of the system. In order to realize the output of the system, what we have to do? Once again, go ahead with the output possibilities, right? So let us take, just carefully observe me, right? Yeah, wait a minute. If it is 0, then here it is become what? Both are complement of each other. If it is 0, then here it is 1. Correct? Yes. Such that this 0 will come here, this 0 will enter here, this 1 will come here, this 1 will enter here. Just I am assuming, if it is 0, then what happens, right? See there, such that we are passing 1 into 1 will become 1. 0 into 1 will become 0. See there, into the SR flip-flop we are passing. Into the SR flip-flop we are passing 1 0. Right? For set pin we are passing 1. For reset pin we are passing 0. For reset pin we are passing 0. Its correspondent output is going to be 1. Guys, listen. I was assuming the past output as 0. But here, when I am assuming the past output as 0, the present output will become 1. Getting me? See that I'm getting 1 now. For the reset pin, I'm having 0. For the set pin, I'm having 1. Its corresponding output is going to be 1. So what is the conclusion here? The conclusion is, so let us consider, let us try and figure out the answer. So if it is going to be 1, automatically here this state will change from 1 to 0. 1 to 0. Let us take the second case. Okay, sir, that is fine. Of course, suppose if I am having 1 here I am having 0. Let's take the opposite case. Suppose inga 1 da irukku inga 0 irukku enthukda. Let us see. Apdiye continue pannalame. Ipo inga 1 vandirukka, ipo inga 0 vandirukka. Let's see. This 0 will go here now. Yeah, this will become 0. This 1 will come here now. This will become, see there, such that 1 into 1 will become 1. 1 into 0 will become 0. Now see there, set pin. Set pin value is what? For set pin we are putting 0. For set pin we are putting 0. For reset pin we are putting 1. For set pin we are putting 0. For reset pin we are putting 1. Such that 1 0 will give you what? 0. So what we have understood? Again it is going to be 0. What about another set? If it is 0, opposite is complement of this one. It is going to be 1. Do you understand? If you are continuing this operation, now what we have understood here? First I am getting 0. Right? First I am getting 0. Right? See there. Guys, listen. If I am considering inga neenga 0 nu assume panningna ungalku see neenga past vandu 0 nu assume panningna present enna varudha complement of the past, correct? Do you all agree with me? Past na 0 nu assume panna present enna varudha complement of past. Suppose na past 1 nu assume panna present enna varudha 0 varudha. It means complement of the past is going to be the output. Complement of the past is going to be the output. Do you all agree with me? See there, when I was assuming 0 I am getting 1. It means what? Complement of this one. This is what? Past output. If I'll take complement, I'm getting 1. So complement of the past is going to be the present output of the system. Anyway, I have understood one thing. Initially, when I was assuming 0, first state it will become 0. Immediately, it is raising its state to 1. Again it is racing to achieve 0. See there, next immediately it is racing 0. Again it is racing to achieve 1. Again it is racing to achieve 0. This is racing 1, that is 1 to 0 to 1. Again racing to achieve 1 to 0. It is running like this. First mela podu thiruma keela odu, thiruma mela odu keela odu, mela odu keela odu. See there, what is this? So case number 1 in the state pathina holding state. Happily if I have 0, 0 is the fixed. That is called DC signal. Just observe. If QN அப்படிங்கிறது it's like a DC. It is fixed. 0 fix பண்ணிட்டீங்கன்னா 0, 1 fix பண்ணிட்டீங்கன்னா 1. That's all. But this is called what? See, this is called holding state, or we can simply call it as memory. This is called reset state. Of course, this is called reset state. This is called set state, because we all know set means 1, reset means 0. But here QN bar, this is called toggling state, or we can simply call this one as race around condition. The problem is, see there, I'm just racing. First time I'm running at 0 condition. Again I'm raising my level. I'm running at 1. Again I'm raising my level. I'm running at 0. Again racing. So we are continuously running, right? So that is called race around condition, right? So we had a problem when we are passing 1 1. Your output is keep on changing its state. That is called toggling. Right? So that is called simply toggling, right? So now I said there was some drawbacks. When I was going up with the SR flip-flop, right? We are using 2 inputs. For S we are using 1 input. For R we are using 1 input, such that in order to set the output as reset or set, output வந்து நீங்க set பண்ணலாம் இல்ல reset பண்ணலாம். In order to do that one, we are using 2 input pins. Right? So one is the R and S. We are using 2 input pins in order to set the output as 0 or 1. Right? So I understood one thing. The thing is, instead of using 2 input pins unnecessarily, you can go up with a single pin that is called D flip-flop, data transmission flip-flop. You can set that things directly. You can set or reset the output just with the help of 1 input. That is the beauty of your data input. That is a data transmission flip-flop. So that's why yesterday, okay, I don't want to talk about that one. So that's why we are going to immediately let me design the D flip-flop with the help of SR flip-flop. Anyway, any flip-flop can be realized with the help of any flip-flop. That thing you have to understand. But in order to let these things, inject these things in the application point of view, I am designing the D flip-flop with the help of SR flip-flop, and immediately I am going to design the T flip-flop with the help of JK flip-flop. That's why then you will get then by just revising the notes itself, you will come to know why we are designing that way. You can also use design. See, T flip-flop can be implemented by D flip-flop, JK flip-flop, SR. Similarly, D flip-flop can be implemented by T flip-flop, JK flip-flop, SR flip-flop. That why I am specifically choosing those things. There will be a reason. That specific reason is, let us take immediately. Now we are going to consider D flip-flop with the help of, I am going to implement D flip-flop with the help of SR flip-flop only. That is the modified version of that is SR flip-flop, right? In SR flip-flop, unnecessarily we are using 2 input pins, right? We can observe the same data just with the help of one input pin, that is called D flip-flop, right? So let us design the D flip-flop. Anyway, listen guys, see, first of all, in order to immediately moving on to the next one, I will have to complete few more things here. We are in JK flip-flop, right? For the JK flip-flop, we designed the truth table now. So what is our next target? We had realized the truth table. Next we have to realize the characteristic table, and then we have to realize the characteristic equation, and then we have to design the excitation table, state diagram. Okay, story might be big. That is very simple task. Let's continue our journey with this. So let me place this excitation table in a side. Now this table I don't want. This table I don't want. Let's place JK flip-flop here. So JK and its corresponding output is Qn plus 1, such that 0 0 0 1 1 0 1 1. Immediately we are going to get Qn here. I think there is 0, this is 1, right? Yeah, this is going to be Qn bar. That is the truth table of JK flip-flop, right? So let us design the characteristic table, right? So immediately our next task, we have to design the characteristic table. We all know characteristic table means we have to consider the present input and the past output of the system in order to guess the present output of the system, right? So let us bring the characteristic table. Yeah, so what I am going to do, we have to consider the present input, past output in order to guess the present output of the system. Anyway, there are 8 combinations, right? They might be 0 0 0, or you can consider 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. Clear? Yes, let us see this one, right? So let us realize these things. Okay. Now what I am going to do, we have to visualize the circuit. So just it's very simple. Listen. What we are going to do, the thing is, here we have 0 0 0. We know characteristic table will be implemented from truth table very simply. What shall we do now? Whenever your inputs are going to be 0 0, present output of the system hardly following the past output. Past output is what? 0. Past output is what? 1. Whenever your input is 0 0, present output simply follows the past output. Now whenever your input is going to be 0 1, present output is simply follows the what? Irrespective of the past, it is setting its value as 0 0. Whenever your input is 1 0, irrespective of the past, it's setting, that is called set, right? And whenever your inputs are going to be 1 1, see then it is not irrespective. Actually, while passing 1 1, it simply follows Qn bar. This is Qn. Qn bar means you have to take complement. If I have 0, complement is 1. If I have 1, complement is 0. Clear? After designing the characteristic table, what is our next task? We have to bring the characteristic equation. Let us bring the characteristic equation also. Fine. Now our next target is we have to achieve the characteristic equation. So for that we are just going up with the K-map only. So consider 8 blocks here. Wait a minute. So let me put it charge. Yeah, that's fine. 1 2 3. Shall we place the values? 0, that is 1. Okay, direct angle. First of all, we have to consider J bar, J. Here we are going to consider K bar, Qn bar, K bar, Qn, K Qn, K Qn bar, K Qn bar. Fine. Shall we register? 0, 1 we have value, 2 we don't have, 3 we don't have, 4 we have, 5 we have, 6 we have, 7 we don't have. Shall we start our journey? Yes, simply we can group these two guys and we can group these two guys, because 4 grouping is not possible, but 2 grouping is simply possible. I can group these two separately, I can group such that only 2 groupings we are going to get the answer simply. Let's write the output. Qn plus 1 is equal to, from this we are going to observe J into the common variable between these two is Qn bar, I hope, plus second case. In this grouping, this is 1, so here we are going to get K bar Qn. Clear? That's all. This is the characteristic equation of the JK flip-flop, right? So let me place them somewhere here. So I got J Qn bar plus K bar Qn, right? Yeah, that is the characteristic equation of the what I can say JK flip-flop, right? So what is our next task? So from the characteristic table we have to design excitation table, right? So excitation table means we have to consider past output and present output. So let us consider past output, present output, such that your possible combinations JK we have to consider, that is excitation table, right? Let us consider 0 0 0 1 1 0 1 1. Shall we proceed further? Yes. See there, whenever your past output to present output, while going from 0 to 0, while going from 0 to 0, while going from 0 to 0, any other possibilities? Yes. While going from 0 to 0, it's possible inputs. For J we are getting 0, for K we are getting 0 or 1. For J we are getting 0, for K we are getting 0 or 1. Let's put don't care. Now while going from 0 to 1, while going from 0 to 1, how many possibilities are there? 0 to 1, here we have the possibility. Any another possibility? Yes, here also we have one more possibility. Let's see its correspondent possible inputs, right? So while going from 0 to 1, if you observe these two things carefully, what we are getting, see there, see there, simply we are going from 0 to 1, 0 to 1, 0 to 1. Its possible inputs are, this is going to be 1. Let's fix J value is 1, whereas K value is 0 or 1. So let's fix X. Now while going from 1 to 0, 1 to 0 enga irukku parunga, this is 1 to 0. We are also having one more here. So 1 to 0, these two, right? Let us consider for J we are having 0 or 1, whereas for K we have 1 1, such that this is fixed, this is X. Now the last possibility 1 1, this one 1 1 correspondent 0 0 here, and 1 1 correspondent 1 0, which is fixed here. 0 is fixed, 0 is fixed. For K we are fixing 0, this is going to be don't care, that's all. This is the excitation table for your JK flip-flop. So immediately after designing the excitation table, our next target is state diagram. So let us design the state diagram also. Since we are bringing the state diagram for what I can say single flip-flop, that is called what I can say JK flip-flop. So we have to consider two persons here, 0 and 1, right? So let's close them first. Let's start our journey. Now see there, past output is 0, present output also 0. I am starting from past output is 0. அப்போ 0ல ஸ்டார்ட் பண்ணோம். present இங்க தான் வந்து முடியுதோ. Its correspondent possible inputs. For J we are giving 0, for K we are giving X. Now while going from 0 to 1, past is 0, present will become 1. Immediately for J we are giving 1, for K we are giving X. Now while going from 1 to 0, this is 1 and this is 0. Its correspondent possible inputs. For J we are giving X, for K we are giving 1. Next, while going from 1 to 1, its possible inputs. For J we are giving X, for K we are giving 0. Clear? This is all about state diagram. Of course, this is all about JK flip-flop. It's over. Now, after completing the JK flip-flop, our next target we have to design D flip-flop and T flip-flop, right? So let us design T flip-flop quickly, right? Okay. Let me design D flip-flop. Yeah. In order to design the D flip-flop, I said I am going up with the SR flip-flop. Guys, listen. In SR flip-flop, unnecessarily we are using two inputs. In order to overcome this issue, we are going up with the we are going up with the what? D flip-flop, right? So we are simply going up with the D flip-flop, right? So let us see its possible outputs. This is simply going to be Qn plus 1. This is going to be Qn plus 1 bar. Now your input is called data transmission, right? So first let us design the truth table. Our first task is we have to design the truth table, right? So truth table in the sense we have input as D, output is going to be Qn plus 1. Now for D you may have two possibilities, 0 or 1. Let's see its correspondent possible outputs. Now the thing is, when we are passing a D as 0, இப்போ நீங்க 0 pass பண்ணீங்க அப்படினா here it will be 0, but what about here? complement of 0 will become 1, such that for in case of that is SR flip-flop, this is SR flip-flop now. So for set we are putting 0. Where is set? This is set. For set we are putting 0. For reset pin we are putting 1. See there, for set pin we are entering, that is we are injecting 0. Whereas into the reset pin we are putting we are injecting 1. Into the set pin we are injecting 0. Into the set pin we are injecting 0. Into the reset pin we are injecting 1, such that a 1-0 combination will give you 0. See there, the entering data is 0, output also going to be 0. So what is the conclusion? It is simply follows. Whichever the data that we are transmitting, that data is being received here. Let's take the second case. If I will pass 1, such that here it will become 1, this is going to be 0. Just opposite case. Set pin value is 1, reset pin value is 0, such that output is going to be 1. Second case. See there, whichever the data that we are passing here, same data that we are receiving in the output, right? But the thing is what? The thing is, listen, here just we are resetting or setting with the help of only one input pin. Unnecessarily we don't use two input pins. So the drawback in the SR flip-flop will be overcome by D flip-flop, right? So let us moving on to the next one. See, after designing the truth table, our next task, immediately we have to design characteristic table. Okay, in order to design the characteristic table, I am in need of present input, past output, and with this we are going to design the present output. So there are 4 possibilities: 0 0, 0 1, 1 0, 1 1. Let us design. But the beauty of the D flip-flop is simply, see that if your input is 0, output will become 0 irrespective of the past. Input is 0, output will be 0. Input is 1, output is 1. Input is 1, output is 1 irrespective of the past. That is what we are getting. Input is 1, output is 1. Input is 0, output is 0. That is the characteristic table. So immediately after designing the characteristic table, we have to write the characteristic equation. Right? So characteristic equation directly we can write. So that is Qn plus 1 is going to be, there are only 2 minterms, one is 1, another one is 1. So here directly it's possible inputs are D into Qn bar plus this one, D into Qn bar plus the second D into Qn, such that if I'll take D outside, it will become Qn plus Qn bar. We all know Q plus Qn bar will become 1. So 1 into D will become D only. So what is the conclusion? Qn plus 1 simply equal to D, right? So let me place the truth table somewhere here in your side. So let us design. Let me keep it here. Truth table for D. Anyway, we can remember this one. For your understanding, I am just placing 1 1. And its characteristic equation is Qn plus 1 simply equal to D. That's all. This is all about D flip-flop, right? So next, after writing the characteristic equation, immediately we have to design excitation table. That is our next task. Class is going good? Any problem? No, I think it's going good. Yeah. So next task is we have to design. This is characteristic table. Now we have to design excitation table, right? So our next target is we have to design the excitation table, right? So this is our next target, right? So fine. Excitation table is what? Excitation means it's very simple. See, this is characteristic table. We all know how to design excitation table, right? So don't wait for me. You please do it now, right? Happily you can do it now because now I am satisfied, right? So we can do by your own now. So let's start. This is excitation table. In excitation table, what we have to do? We are going up with the present output and past output. Happily we can design the input now, right? So there are 4 possibilities: 0 0, 0 1, 1 0, 1 1. But the thing is, whenever we are going from 0 to 0, see there, past is 0, present also will become 0. Past is 0, present also will become 0. It's possible. Corresponding input is 0 only. Now past is 0, present become 1. Past is 0, present, past is 0, present will become 1. Corresponding input is 1, of course. Now past is 1, present is 0. Past is 1, present is 0. Corresponding input is 0. Past is 1, present also will become 1. Corresponding input is 1. This is excitation table of your, what I can say, D flip-flop, right? Excitation table of D flip-flop. Okay, fine. At last, what do we have to design? We have to design state diagram, right? So that is the, that is the final step that we need to do. Okay, what we have to do? State diagram. So we have to design state diagram. Okay, fine. How will you design? See there, once again we are considering single flip-flop. So there are single bits 0 1. Let's see. Present output is 0. Past output is 0. Present output also will become 0. Past output is 0. Present also will become 0. When your input of the D flip-flop is possible input is 0. Now past is 0. Present will become 1. past is 0, present will become 1, its corresponding input of the D flip-flop is going to be 1. Now past is 1, present will become 0, corresponding input of the flip-flop is going to be 0. Past is 1, present also 1, its corresponding input of the flip-flop is 1. Clear? So that is how we are designing the state diagram of the what I can say D flip-flop. Okay, so next step, immediately we have to design the next flip-flop is, so let me rub these things. What I have to do, we have to design the T flip-flop, right? So our next target is we have to design the T flip-flop, right? So let me remove these things. Okay, now we have to design T flip-flop, right? Yes. Now listen guys, in JK flip-flop we observed a condition is called race around condition, that is simply we are calling it as toggling, right? Now sometimes race around condition will be the problem for us. Actually it is the problem, but we can overcome. And the race around condition வந்து நம்ம கொஞ்சம் ரெஸ்ட்ரிக்ஷன் கொடுத்து டாக்லிங் மோட்ல ஒரு பர்ஃபெக்டான ஸ்டேட்ல வந்து உங்களால வந்து சர்க்யூட் வந்து ஆக்ட் பண்ண வைக்க முடியும். See what I would like to conclude, very simple. நம்ம வீட்ல வந்து LED பல்ப்ஸ் வந்து நீங்க அப்சர்வ் பண்ணி பார்த்திருப்பீங்க. இப்போ சம் LED பல்ப்ஸ்லாம் எப்படி இருக்கும் அப்படின்னா கலர் வந்து சேஞ்ச் ஆகிட்டே இருக்கும். ஆனால் வெளியில இருந்து நம்ம பார்க்கும்போது எப்படி இருக்குன்னா அந்த லைட்ஸ் வந்து அப்படியே ரன் ஆகிட்டு இருக்க மாதிரியே இருக்கும். நம்ம வீட்டில் மோஸ்ட்லி எல்லார் வீட்லையுமே அது இருக்கும், ரைட்? ஸோ கலர்ஸ் இப்போ நம்ம ஒரு 3 or 4 கலர்ஸில் வந்து நம்ம பல்ப்ஸ் வந்து டிசைன் பண்ணியிருப்பாங்க. அது பார்த்தீங்கன்னா எப்படி இருக்கும், இட் இஸ் கீப் ஆன் ரன்னிங், லைக் ரெட் ப்ளூ எல்லோ கிரீன், லைக் தட் ரெட் ப்ளூ எல்லோ கிரீன், ரெட் ப்ளூ எல்லோ கிரீன். அது என்ன இருக்குன்னா லைட் ஆக்சுவலாக என்ன ஆகுனா ஃபர்ஸ்ட் இங்கே ரெட் ப்ளூ எல்லோ கிரீன் ஃபிக்ஸ் பண்ணியிருக்கீங்கன்னா அடுத்து ரெட் ப்ளூ எல்லோ கிரீன், அடுத்து ரெட் ப்ளூ எல்லோ கிரீன், ரெட் ப்ளூ எல்லோ கிரீன், ரெட் ப்ளூ எல்லோ கிரீன் அப்படி ஃபிக்ஸ் பண்ணியிருப்பாங்க. அப்போ என்ன ஆகுனா ஆட்டோமேட்டிக்லி சீக்வன்ஸாக இந்த பல்ப் ஆஃப் ஆகும்போது அடுத்து அது எரியும். அடுத்து அப்போ என்ன ஆகுனா நீங்கள் வெளிலேருந்து பார்க்கும்போது தட் சீக்வன்ஸ் வந்து எப்படி இருக்குன்னா தே ஆர் ரன்னிங். பிகாஸ் அவங்க ஃபர்ஸ்ட் இது ஆஃப் ஆனோடனே அடுத்து அது ஆன் ஆகும். ஆஃப் ஆன் ஆஃப் ஆன், இந்த சீக்வன்ஸ் வந்து அப்படியே போயிட்டே இருக்கும், ரைட்? ஆஃப் ஆன் ஆஃப் ஆன் ஆஃப் ஆன் ஆஃப் ஆன். அப்போ உங்களுக்கு வெளிலேருந்து பார்க்கும்போது எப்படி இருக்கும், இட்ஸ் ரன்னிங். Simply that is we can observe. This is just I am giving example, that is called toggling mode. அப்போ toggling mode ல நமக்கு application இருக்கா இல்லையா? Of course toggling mode application will be there, but in JK flip-flop once again if you want to go ahead with, if you want to achieve the toggling mode either you can done with the help of JK flip-flop, you can also done that one with the help of T flip-flop. But the conclusion is in JK flip-flop I mean of 2 inputs, but in T flip-flop with 1 input you can achieve. So the conclusion is now I would like to design the T flip-flop with the help of JK flip-flop. Now the motto, my motto is, I told you any flip-flop can be implemented with the help of any flip-flop, but my motto is I would like to let you I would like to let you all to understand why I am designing this T flip-flop with the help of JK flip-flop, because in back of the JK flip-flop there was some drawback. That drawback is overcome by T flip-flop, right? So with the help of single input we can bring out that toggling mode, right? So let us design the T flip-flop, right? So we are going to design T flip-flop, right? Fine. So in T flip-flop what we are going to do, let us see. This is J, this is K, this is going to be T, right? Yeah. Once again, let me consider this one as Q1 plus 1, Q1 plus 1 bar, right? Fine. So what is our next task? So immediately we have to design truth table for this system, right? So that is going to be truth table. Clear? So in this truth table, what we are going to observe, see there, whenever we are passing, but T flip-flop, right? So truth table means input is T, output is Q1 plus 1. Let us see the possible inputs and output combination. See there, if your T value is 0, automatically what will happen? If I pass T is 0, so it will become 0, it will also become 0. So see there, actually in the outside we are having T flip-flop, but in inner structure we have JK flip-flop. If I pass 0, both are 0 0. In JK flip-flop, whenever we are passing 0 0 as the input, output will become Q1. அதாவது pastல இதுக்கு முன்னாடி என்ன ஸ்டேட் இருந்ததோ that will become here. Either it might be 0 or 1, past என்ன இருந்தது அப்படியே presentல வந்துடும். Suppose if you are passing 1, if I'll pass 1 here, if I'll pass 1, automatically will become 1, it will also become 1, such that JK, both are going to be 1 1, its possible output is going to be what? Qn bar. Clear? We have to, this is called about, that is the truth table of your T flip-flop. Now what is our next target? Immediately we have to design the characteristic table. So characteristic table means I need present input and past output in order to design the present output of the system. So 0 0 0 1 1 0 1 1. Shall we design? Of course it's very simple. See there, if your input is 0, if your input is 0, then flip-flop, present output of the flip-flop simply follows the past output. Past output is 0, past output is 1. Whenever your input is 0, then present output of the flip-flop simply follows the past output. Whenever your input is 1, then present output of the flip-flop is going to be the complement of the past output, such that this is going to be the output of the system. This is going to be the output of the system. I hope things are very clear to you all. This is called characteristic table. Now let us immediately design the characteristic equation. Now what will be the characteristic equation? The characteristic equation can be written as Qn plus 1, right? K method does not require, simply two minterms are there, you can directly write. So that is T bar Qn plus T Qn bar, or you can directly realize that is what T XOR with the Qn. Clear? That's all. So the characteristic equation of the D flip-flop is what? T Qn bar plus Qn T bar, of course. Right? So immediately after designing the, that is after writing the characteristic equation, our next target is we have to write excitation table. So let me write excitation table also. Let us write the excitation table also, right? Excitation table, right? So in order to design the excitation table, the conclusion is, let's see, excitation table enna பண்ணுவீங்க, I mean it of past output, present output in order to write the input of the system, such that we have to consider four possibilities: 0 0 0 1 1 0 1 1. Let us see, whenever we are going from 0 to 0, that is Qn is 0, Qn plus 1 also, while going from 0 to 0, T value is 0. While going from 0 to 1, while going from 0 to 1, T value is 1. Now while going from 1 to 0, while going from 1 to 0, T value is 1. Now while going from 1 to 1, T value is 0. This is going to be the excitation table. Now immediately after designing the excitation table, we have to implement the state diagram for this system. Yeah, I think the class is going good. Fine. So our next target is we have to design the state diagram of the system. Yeah. So in state diagram, once again we have to achieve 2 bits, 0, 1. Shall we start? Yes. See, past output is 0, present output also will become 0. Past output is 0, present output also will become 0, such that its correspondent input is 0. Past output is 0, present output will become 1. Past output is 0, present output will become 1. Its correspondent input is 1. Past output is 1. Present output will become 0, such that its correspondent input will become 1, such that past is 1, present also will become 1, its correspondent input is 0. Clear? That is going to be the state diagram of the system. Clear? That is going to be the state diagram. I hope things are very clear to you all. This is all about flip-flop circuit design, right? Now I hope things are very clear to you all, right? Apart from that, now we have to understand one more thing. You all have read one more term that is called master-slave flip-flop. Now let me explain that one clearly. Actually the conclusion is, in JK flip-flop, I said there was some drawback. நீங்க ப்ராப்பரா வந்து 1 1 JK flip-flopக்கு நம்ம 1 1 பாஸ் பண்ணும்போது என்ன ஆகும் அப்படின்னா, actually your output, that term is called race around condition only. நீங்க ப்ராப்பரான டைம் பீரியட் வந்து செட் பண்ணல அப்படின்னா there is some problem will occur. That is called what? Race around condition. Automatically நீங்க வந்து அது என்னன்னா toggling modeல ப்ராப்பரா செட் பண்ணணும். If you are unable to set that is a toggling mode properly, automatically what will happen? Race around condition will happen, right? So in order to overcome that drawback, and the overcome race around அப்படின்னா 0 ல இருந்து 1 போகுது, 1 ல இருந்து 0 immediately that state of the circuit is keep on changing. That is called toggling. So in order to avoid that one, we are going up with அப்போ நம்ம என்ன பண்றோம் அப்படின்னா JK flip-flop வந்து 2 times வந்து நம்ம கன்சிடர் பண்ணி we are attaching them together such that with the help of clocks, because what is the advantage of flip-flop? In flip-flop, with the help of clock we can control the circuit. flip-flop வந்து நீங்க என்ன பண்ணிக்கலாம், clock வச்சு கண்ட்ரோல் பண்ணிக்கலாம். So clockல வந்து there are two possibilities, right? So let's see, let me design the master slave flip-flop, right? So in JK flip-flop there was a simple issue that is called race around condition. In order to overcome the race around condition, we are moving on to the master slave flip-flop, right? So the master slave flip-flop is the modified version of JK flip-flop only, right? So in the JK flip-flop, whenever our inputs of the JK flip-flop is going to be 1 1, there was some drawback in the system, right? So let us consider. Let me consider that things. So let us remove this one. So whenever the system is going to be, see, this is our JK flip-flop. So let me consider JK flip-flop, and let us consider one more JK flip-flop, right? So let us consider one more JK flip-flop. Now your inputs of the JK flip-flop. So let me consider master flip-flop. This is going to be the master JK flip-flop. Its corresponding input let me call JM and KM. Similarly, its output is going to be the input of the slave flip-flop. Input of the slave flip-flop. This is Qn plus 1 only. This is Qn plus 1 bar. Immediately this is going to be the output. This is the point where we are going to receive the output now. With this I am introducing one more person, that is called clock. Right? Let us see what happened now. So for an example, first case, anyway we are facing the issue, keep the heading master slave flip-flop. We are discussing about master slave flip-flop. Okay, master slave flip-flop. In master slave flip-flop, see we had a problem in JK flip-flop with the 1-1 input. 1-1 pass பண்ணும்போது output ல என்ன வந்தது? We had a problem. So let's see what happened. So when we are passing 1-1 as the input, right? So let us see, clock value is 1. For example, clock value is 1. Immediately assume this is the first circuit. இப்போ என்ன ஆகுதுன்னா, நீங்க 1-1 first clock கொடுக்கும்போது என்ன ஆகுதுன்னா, here it is become, guys listen, actually this clock is going 1 to 0, 0 to 1, it's keep on like this. First understood, when we are passing 1 here, what will happen? 1-1 will come here, it's possible output. For an example, here we are getting 0, here we are getting 1, first case. And then what will happen? See there, இப்போ இங்க 1 கொடுத்தீங்க அப்படின்னா this clock இங்க 0 வரும், such that 0 இங்க enter ஆகும். இந்த slave flip-flop turn on ஆகாது, it won't turn on. Why? Because see there, here we are giving high input, but here we are giving low input. Now this circuit won't be turn on, right? If we want to turn on, we have to pass 1 electrical pulse. We should pass in order to turn on this circuit. We are not passing electrical pulse, that is ground is 0. We are not passing any electrical signal to turn on this circuit, but this circuit will turn on because we are passing electrical signal. If I pass electrical signal through this circuit, immediately what will happen? See there, if you have 1-1, either you may get 0-1 or 1-0. Just to consider one possibility, that's all. If it is 0-1, see there, now this 0 will come here, this 1 will come here. Then what will happen? And then see there, once this output we are receiving here, and then I am going to change, right? Now I am giving 0 here. Now what will happen? This master flip-flop will be turned off automatically. 0 will come here, it will become 1. Slave flip-flop will turn on. Once your slave flip-flop will turn on, let's see what will happen. While passing 0-1, see there, JK flip-flop, this is JK flip-flop, right? When your J value is going to be 0, right? J value is going to be 0 and K value is going to be 1. 0-1, it's possible correspondent output is going to be 0. Its correspondent output is going to be 0. If it is 0, automatically here it will become 1. That's all. Now the thing is, again without giving gate pulse, நீங்க திரும்பவும் இங்க gate pulse apply பண்ற வரைக்கும் there will be no changes in the output state of this circuit. It won't toggle, it won't go like 0-1 0-1. That state is not possible. It will be fixed now, right? See there, it will be controlled with the help of clock pulse. It is hardly depending on the clock pulse only, right? So only depending on the clock pulse, right? So with the help of clock pulse, automatically you can fix the state of this circuit without facing that race around condition issue. Clear? That is all about master slave flip-flop. But the thing is, you'll have to understand, see, actually in the output state we are facing the race around condition like this. It is keep on going like this. Correct? Your state is keep on 0 to 1, 1 to 0, 0 to 1, 1 to 0, 0 to 1, 1 to 0. This is race around condition. Just we are racing. We are going from 0 to 1, again 0 to 1, again 1 to 0, 0 to 1, 1 to 0, 0 to 1, 1 to 0, 0 to 1. It's keep on going. That is simply called race around condition. Now the thing is, now for an example, here I am passing a clock pulse. இப்போ நீங்க என்ன பண்றீங்கன்னா இங்க ஒரு see this is calling என்ன நடக்கும் அப்படினா see there, actually here it's happening, it's because of there was some delay in the circuit, right? So anyway, let us assume in order to overcome this issue we have to set, இப்போ இந்த race around condition வந்து நடக்கிறதுக்கு வந்து ரீசன் என்ன அப்படினா in your circuit, right, input sideல வந்து என்ன ஆகும் அப்படினா in your flip-flop your data is keep on changing. கரெக்ட்டா? feedbackல இருந்து data backல வருது, திரும்ப வந்து system வந்து output சேஞ்ச் ஆயிட்டே இருக்கு. கரெக்ட்டா? inputல data சேஞ்ச் ஆகுது, outputல immediately changing. So see, this is fixed, 1-1 is fixed, fixed. But what about output, right? Input நீங்க 1 1 கொடுத்துறீங்க, but feedbackல நீங்க 0 வந்தா 0 will come back, it will change the property of the system, again it will become 1 1 to 0 0 to 1, it's keep on toggling, right? So that is called what? So there will be some error, right? So there will be some delay into the system, that is called propagation delay, right? Actually we are facing these issues with because of the propagation delay, right? So let me explain all those things in future. Right now just observe. நீங்க என்ன பண்ணணும் அப்படினா, you will have to design your clock such that நீங்க clock வந்து எப்படி டிசைன் பண்ணணும் அப்படினா, your designed clock value should be less than or equal to the value of propagation delay of the system in order to overcome this issue. What do I mean? The thing is, for an example, இப்போ வந்து நீங்க ஒரு லாஜிக் கேட் எடுத்துக்கிறீங்க, அந்த லாஜிக் கேட்ல வந்து பாத்தீங்கன்னா டிலே வந்து எவ்வளவுனா 10 nanosecond. அப்படினா மீனிங் என்ன? See, that is not a propagation delay. Let us just assume that is propagation delay. Not see, I am not telling that not. Actually there is some delay. ஒரு கேட் இருக்கு, அதுல some delay இருக்குன்னு வெச்சுக்கோங்க. அப்ப என்ன ஆகும் அப்படின்னா, நீங்க என்ன பண்றீங்கன்னா, நீங்க 0 பாஸ் பண்றீங்க. 0 பாஸ் பண்ணோன்னே என்ன ஆகும் அப்படின்னா, யுவர் கேட் உங்களோட ஃபிளிப் ஃப்ளாப் வந்து என்ன பண்ணுது அப்படின்னா, 0 வந்து ஒரு 5 செகண்ட்ஸ்க்கு அப்புறம் வந்து 1 ன்னு மாத்தி விட்டுரும். கரெக்டா? ஆஃப்டர் 5 செகண்ட்ஸ் நீங்க பாஸ் பண்ண 0 வந்து கரெக்டா 1 ன்னு மாத்திரும். இப்போ நான் என்ன சொல்றேன் அப்படின்னா, 5 செகண்ட்ஸ்க்கு முன்னாடியே வந்து நீங்க திரும்பவும் கிளாக் வந்து கண்ட்ரோல் பண்ணிட்டீங்க அப்படின்னா, ரைட், வித் தி ஹெல்ப் ஆஃப் தி கிளாக் ஒரு 4 செகண்ட்ஸ் இல்ல 3 செகண்ட்ஸ்லேயே வந்து நீங்க சர்க்யூட் வந்து கண்ட்ரோல் பண்ணிட்டீங்க அப்படின்னா, அங்க என்ன ஆகும்? திஸ் சேஞ்சிங் won't occur. Are you getting me? நீங்க என்ன பண்றீங்கன்னா, நான் உங்களை மட்டும் தனியா விட்டா நீங்க படிக்கவே மாட்டேங்கிறீங்க. நான் பக்கத்துல வந்தா என்ன பண்ணுவீங்க? ஆட்டோமேட்டிக்கலி ஐ அம் ஜஸ்ட் ஃபோர்சிங் யூ, ஜஸ்ட் டேக் யுவர் நோட்ஸ் ப்ளீஸ், ரிவைஸ் அப்படி சொல்லிட்டே இருந்தா என்ன ஆகும்? அட்லீஸ்ட் ஏதாச்சும் ஒரு கடுப்பாக்கியாச்சும் நோட்டை திறந்து வச்சு உட்காந்துட்டு இருப்பீங்களே, தட் வில் ஹேப்பன். தி திங் இஸ் ஹியர், அவுட்புட்ல வந்து என்ன ஆகுதுன்னா, ஸ்டேட் வந்து சேஞ்ச் ஆகிட்டே இருக்கும் வித்வுட் தி கண்ட்ரோல். நவ் வென் வி ஆர் புட்டிங் கிளாக் வந்து நான் பாஸ் பண்ணிட்டு அந்த டிலே வந்து நான் கண்ட்ரோல் பண்றேன். டிலே வந்து 10 செகண்ட்ஸ் இருக்கா, நான் 8 செகண்ட்ஸ்லேயே வந்து அதை ஆஃப் பண்ணிடுறேன். 10 செகண்ட்ஸ் வரைக்கும் நீங்க விட்டா தானே சேஞ்ச் ஸ்டேட் ஆகும். சேஞ்ச் வந்து ஸ்டேட்டோட சேஞ்ச் வந்து ஐ மீன் ஸ்டேட் will change when we are waiting for 10 seconds. நான் 8 செகண்ட்ஸ்ல கொடுத்துறேன்னா 10 செகண்ட்ஸ் வரைக்கும் போகாது. திரும்ப என்ன ஆகும்? நீங்க ஸ்டேட்டை கண்ட்ரோல் பண்ணிட்டீங்க. once again new state will occur, again your gate will wait for 10 seconds. அடுத்த 10 செகண்ட்ஸ்க்கு அப்புறம் தான் டிலே வெளியில வரும். நான் திரும்ப என்ன பண்ணுவேன்? 10 செகண்ட்ஸ்க்கு முன்னாடி 8 செகண்ட்லயே போயிட்டு திரும்ப ஸ்டேட்டை கண்ட்ரோல் பண்ணிடுவேன். once again திரும்ப அது 0ல இருந்து ஸ்டார்ட் பண்ணி 10 செகண்ட்ஸ் வரைக்கும் போகும். அது 8 செகண்ட்ஸ் ரீச் பண்ணும்போது திரும்ப நான் அதை கண்ட்ரோல் பண்ணுவேன். such that we are continuously pushing the system and we are controlling the delay. That is what I can say, race around. Clear? That's it is over. This is all about master slave. Simply observe. The thing is, there is a term is called race around condition. That condition will be controlled with the help of master slave flip flop. It's over with this, right? So flip flop circuits are completely over with this. There is one more small topic that I left, right? That is we have not seen the conversion procedure. I told you you can design any flip flop with the help of any flip flop. Of course we have done in that same way only, right? Whichever the systems that we have gone through, that we have gone through, I will take all those things in our next class, right? We will design the rest of flip flop, like we will see how to design all flip flop from, that is any flip flop from any flip flop. So with this, let's wind up the today class. I hope you all understand now the flip flop circuits. If you have any doubts, you can ask your doubts in the group. Okay, let's wind up the class. Thank you all.